Yes, so I was mentioning Ontopic s.r.l, which is a spin-off we founded 3 years ago, which tries to bring to industry some of the ideas that I will be talking about today related to managing data using ontologies. And to make practical means, as I was saying before to begin, that my presentation will be less theoretical than the very nice talks that we had today in the past days. I hope it will not be too basic, again, compared to the previous presentations. So in that sense, this is more practical. But I will not be talking about what we really do in the company. So what I will be talking about is essentially the result of the work in my research group, and not only in my research group, but also in other groups working on this topic of data management using ontologies. And we have been working on this topic since theoretically since 15 years, practically in the sense of developing tools and technologies since 10 years, so that the tools that we have developed are now quite well engineered. And I hope I will give you some ideas about this in my presentation. Umeå is also an affiliation where I'm part-time. So I'm part-time in Umeå in northern part of Sweden, and where I'm also building up a research group, and some of the PhD students are also here. Romuald and Livia are here. They come from Umeå. Okay, I think you have seen this variation of this picture hundreds of times in different colors, in different sizes and whatever. This talking about data management where several issues become important. Typically, volume is considered important, but volume is not the only aspect. In fact, we are dealing here more than with volume, with variety of the data, which is related to the fact that data has a complex structure, and we need to take this into account when we want to manage data. Then there are also the other aspects. Veracity plays also an important role in the context of ontologies, because ontologies are logical theories that deal with somehow the quality of the data. One of the qualities of the data is related to whether the data is consistent, is true in some sense. So this is also an important aspect, although I will not say too much about that point. I will not say anything about velocity, which is also an important dimension, namely related to the fact that data changes, and there is a lot of work, and there will be a lot to say about dynamic data, so data changing over time, because in fact, this is what data always does. I mean, no data is static in reality. Data evolves, and we need to take this into account. But, okay. So one point that I wanted to make is that, and this is also has been assessed in industrial settings, is that the volume is not the key aspect in general. A key aspect is the fact that data has a complex structure. So the variety is the key aspect. This is relates to some survey that has been done now quite some years ago, but this is still valid. So when companies and large corporations or large organizations who have to deal with data look at the challenges, the biggest challenge comes from variety of the data. And what I want to say today, and the technology you have been developing, try to address this point. Now, let me provide a brief motivating example for what I will be saying, so for ontology-based data management. And this is related to the fact that in large corporations, in large organizations, a key aspect is that of getting to the right data, so bringing the right data to the right people, and then also establishing the quality of this data. And the example I want to make is from the oil and gas domain, where we had some years ago quite large European projects with the big industrial partners. One of these industrial partners was Equinor. At that time, it was called Statoil, which is the biggest Norwegian oil company. I mean, they are the leaders in drilling oil on sea worldwide. And they have large teams of data engineers. They have also large teams of geologists who have to analyze the data. And in that setting, the engineers, and these are geologists and geophysicists, so these are not computer engineers, they spend a large amount of their time on the problem of getting the access to the right data so that they can study and analyze this data and get the information, the useful information they need in order, for example, do predictions about drillings they need to make. And the example I want to make is precisely about the department of Statoil exploration. so Equinor exploration now, where geologists need to access, before drilling new well bores, they need to understand where they should do the next drillings. And for that, they need to gather relevant information about previous drillings and analyze this data so that they can then give suggestion where it is more likely that they will find oil. And for that, Statoil or Equinor maintains a large relational database. It's called SLEGE, which is not so large in terms of size if we compare it to the big data now maintained, for example, by social networks and so on. But it's still large in terms of size. It's terabytes of relational data. But what is challenging is the complexity of this data. So this database consists of more than 1,500 relational tables, each with dozens of or hundreds of attributes, and more than 1,700 views that are built over these tables. And on this database, in Equinor work 900 geologists, so they need to access this data. And for example, here we have a simple extract of an information request that such geologists might have. So they would like, in some geographical area of interest that they characterize, they want to return, get all the pressure data tagged with some stratigraphy information, with some control attributes that they are aware of and they know, and also they need to apply further filtering on it. Now, a geologist poses the question roughly in these terms, so in essentially natural language. But then to obtain the answer to this question, they need to access this SLEGE database. And this, which means they need to translate their request into SQL, which is the language with which you access such a relational database. Now, in order to get the answer to this query, they need to access a main table for wellbores, which has 38 columns. And if you try to look at this table and the names of these columns, you will not understand anything. So this database uses cryptic names, both for the tables and for the attributes in this table. Then to obtain the pressure data, which is also part of this request, they need to do a join with 4 additional tables and apply some filtering conditions. And then to obtain the stratigraphy information, they need to join the table so far with 5 more tables. Okay, so if you put things together, you get a quite complex SQL query that is written here, and that makes use of these tables with their attributes. Now, obviously, the engineers, so the geologists, they are not able to write this SQL query. It's not their business. They are not computer scientists, so they would never be able to write this query. So what they do, in general, they go to a data management expert. So Statoil has several data management, so data specialists. So these are people who are computer scientists and know well the database, know well how to access it, but also have gained experience in this domain, in the oil and gas domain, because they need to understand what the geologists are talking about. So the geologists come with their request, the one that we saw on the previous slide, and then these data management experts, they translate this request after several iterations with the geologists into the SQL query that you see here. And this whole process can take up to several days. So it's not something that they do on the spot. I mean, it's complicated. You have to deal with 3,000. So this is a costly process. And then this process typically is iterated because the geologists get the answer then to their query. This is being executed. They analyze, they look at the data, and then they see that they need additional, apply additional filters, maybe additional conditions. So this whole process iterates. So this is a quite costly effort, and that requires interaction between costly experts. Geologists, they are highly paid engineers, also data management experts. And they need to have a deep knowledge about this data and also about the domain. And this whole thing is quite costly, as I was saying. This costs Equinor roughly 50 million euros per year, just this problem. So just dealing with the data access problem in this department with 900 geologists. And at that time, so we looked at this several years ago, this was a motivation for starting this European project in which Statoil was one of the industry partners, and in which we were trying to push the technologies based on ontologies for solving precisely this issue. So how do we address the challenges that come from, for example, this use case? But a similar problem occurs in many other settings. Think of large banks, of public administrations. So this is very I don't know in European countries, but I guess it's the same in Italy. There's a huge effort towards the digitalization of the public administration. And also there are huge problems related to also integrating data coming from different departments, different ministries is a challenging problem. Now, the idea that was proposed at that time, that we proposed in that project, but that has been pursued also in other settings, is to address the problem by using domain knowledge, specifically encoded in ontology. So the idea is to use a global schema, but this global schema is represented in terms of an ontology, because this ontology exposes the information, the relevant information, the data in terms of a graph, what we call now a knowledge graph. So this information is exposed through the ontology to the users, but then this ontology is mapped to the actual data sources. So we use this global schema in terms of an ontology and map this global schema to the actual data sources. And the ontology exposes it as a graph, which is a flexible data model. So the approach that we took there is not to use traditional data integration technology, which exposes relational data in general. So traditional data integration, this global schema is a relational schema. Instead, the idea is to use a graph model, so a knowledge graph, because it gives more flexibility in integration. And then a further point that was pushed in this work and we are pushing is to do this integration in a virtual way. So we don't materialize the integrated data into into a data warehouse, which would be relational, or a knowledge graph, a materialized knowledge graph, but we keep this integrated information virtual. So it's not materialized. And if you put together these ideas, you get to this virtual knowledge graph approach to data access integration, which we now call in this way. So we call this technology virtual knowledge graphs. But for a long time, and still it's been known as ontology-based data access and integration, for the obvious reason that this knowledge graph is presented through an ontology to the user, and the underlying data sources are connected with ontology. So that's how we also call it. And you find a lot of papers, a lot of work, also our own work, and this keyword of OBDA or OBDI, if the integration aspect has to be emphasized. So if we just put together these ideas, we get to the architecture, conceptual architecture as is depicted here, where we have here at the bottom level, the data sources. And now the setting that we assume is one where we present at this level a relational view of this data source. So these data sources in general can be quite heterogeneous. So can be relational databases, but also CSV files, JSON documents, XML or Excel files, CSV files, so various kinds of data, and even web services. But still, what I'm saying today, and the setting that I'm addressing now, I assume that we have a layer, a low-level layer somehow that exposes this data in terms of a relational schema. Okay? And there are several federation tools, also commercial ones, Denodo, Dremio, Tade, just a few of them, but there are dozens of such federation tools that provide such a relational view of the underlying data, which is quite conceptually quite simple in the sense that all the data sources are put together and each one is just exposed relationally, okay, in a quite natural way. Then these sources are mapped to an ontology, to the virtual knowledge graph that you see depicted there, which is constituted by a component that is the ontology itself. The ontology defines essentially the vocabulary that is shown to the user, which is typically a vocabulary in a language that is in which the users are familiar. So, for example, it would use terms that are familiar to these geologists. So terms coming from the oil and gas domain if you're integrating data sources from that domain. So the ontology is the component that is exposed, but then the mappings that are the intermediate layer between the ontology and the data sources, they essentially expose the data in the sources in terms of a knowledge graph that is formulated using the terms of this ontology. And then users, which could be either human users, but also applications that leverage the integrated data, they issue queries to this virtual knowledge graph system. And the idea is that these queries, which come from various applications or users, they get translated by the system into queries down to the data sources, and the answers are provided to the users. Okay, so that's the idea. And I want to discuss the various components of this general architecture. But before I do so, and I will do so today, let me briefly motivate some of these points. I already said something, but let me here summarize it again. So why an ontology? So why do we use an ontology for the global scheme? I mentioned this already. An ontology in general is a structured formal representation of certain concepts that are relevant for a domain of interest and the relationships between these concepts. And in this setting, the ontology has essentially a twofold purpose. It defines this vocabulary of terms that are relevant for the domain of interest and that are the terms known to the users. And these terms are essentially classes and properties that are exposed to the user. Carsten this morning talked about concepts in description logics and roles in description logics. Is just nothing else than classes are concepts and properties are also called roles, depending on whether you take a more somehow theoretical approach in terms of description logic, or you go more to the semantic web terminology where ontologies are, and the elements of an ontology are called in this way. Then the second purpose of the ontology is to extend the information in the data sources with domain knowledge. So the ontology encodes relevant domain knowledge. So the data is enriched with this knowledge, and this knowledge can be used at query answering time, at query processing time, in order to provide additional answers. And Carsten was talking about this extensively this morning. All the reasoning that we do with ontologies is this kind of enrichment of the answers. Okay.
Sorry, so you need experts of the domain, for example?
Sorry?
You need experts of the domain?
Yes, obviously this is an issue. This ontology requires expertise about the domain in order to encode correctly and in a possibly complete way the domain knowledge. This is in general not an easy task. So because these ontologies can become quite complex, so they can have themselves hundreds of classes and properties when they have to encode a complex domain. Okay, so but this we'll see this is not the only aspect. The second aspect will be the mapping component, which I'll talk about, about which I'll talk in a second. But the advantage of this setting is that, in fact, one can also rely on a lot of work that has already been done. So there are many available standard ontologies over various domains that one can use and one can leverage in this setting. And ontologies also at various levels. So-called, domain ontologies that are of the type that I was mentioning before, but also so-called upper level ontologies, which are somehow more abstract ontologies that define more general abstract properties of classes and properties that are present in an ontology and can be used in order to assess the quality of the other components of the ontology. So there are many ontologies that are available and can be used for this activity. But this doesn't mean that in general one can just rely on such available ontologies. So this requires, as we were saying, also in general quite some commitment to build a customized ontology for specific domains. Okay. And this is one of the challenges in this setting. So it doesn't come for free. It requires somehow a commitment to develop or to invest in the development of this ontology. And this is not an effort that you do in one day. Developing such complex ontologies can require several months of work of domain experts in general, who have to interact also with ontology experts, because one group of people knows the domain and know what knowledge they want to encode, but they might not know how this ontology should be built. So this is a challenge in general. Now, the second aspect I want to mention is why do we use a knowledge graph? As I was mentioning before, the traditional approach is to adopt a relational global schema, but a knowledge graph gives more flexibility. So it doesn't require to commit to a certain structure a priori, because committing to a relational structure can be quite binding if you have a long-running project. Also, a graph is able to better deal with heterogeneity, which is an important aspect in this setting. Also, with missing information or incomplete information. And when new information comes, this is also an important aspect. In general, having a graph does not require to do complex restructuring operations that you would have to undergo if you commit to certain relational structures. So it has some advantages. The other aspect are the mappings. Now, what are these mappings? I will talk extensively about the mappings in this tutorial today. But essentially, these mappings are declarative specifications. And again, in the traditional approach to data integration, the connection between the APA schema, the global relational schema, and the data source is often done in a procedural way through code that extracts the information from the sources and exposes it in terms of the global relational schema. Instead, mappings are not code, they are declarative. And this has several advantages. First of all, they are easier to understand and hence to design and to maintain. They support an incremental approach to integration, as we will comment and see. And also, being declarative, they are machine processable. So one can reason over such mappings and can use them in order to automate certain processes. And this is heavily exploited in this setting. Yes?
Whenever you say knowledge graph, this is a synonym to FDL ontology?
Yes, so take it as a synonym of somehow the T-box of ADL ontology, but then together with the T-box, and I will talk about this, you have the A-box that is, however, not a materialized A-box, but is an A-box that is virtual in the sense that it is constructed from the data using the mappings. Okay. So this idea of knowledge graph combines both the T-box plus this data that this A-box that is presented in a virtual way. Now, this is more, I mean, I must admit it clearly. So the fact of talking about knowledge graphs and virtual knowledge graphs is a marketing issue because the term knowledge graph is nowadays popular. I mean, there's the Google knowledge graph, Facebook has a knowledge graph and so on. So if you talk to industry people mentioning knowledge graphs, they become immediately interested. If you talk to them saying you do ontology-based data access, they don't know what this is about and probably are not interested. So it's a marketing move that helps to communicate to people that we hope to convince to adopt this technology. Now, the last point that I want to briefly discuss is this virtualization aspect. So in general, again, in traditional data integration, mostly data integration is done through what is called the ETL approach, the extract, transform, load approach, in which data is extracted, materialized, so extracted in a material way from the sources. It's processed, transformed, and then is loaded in a materialized global schema, typically a data warehouse, but also in the setting where you want to use knowledge graphs, it could be also a materialized knowledge graph. Okay. Instead, in the virtual approach, we don't do this. So we keep the data at the sources. So data stays in the sources and is only accessed at query time when requests are issued to the integration system. These requests are translated down to the sources and the data is extracted at that moment on the fly and provided as an answer to the user. So this avoids to construct a potentially quite large and costly to maintain knowledge graph or data store and to keep it updated, because that's a key issue in general. When data evolves, if you materialize integrated data and the sources evolve, then you need to rematerialize the data in an incremental way, but this is a costly process in general. Having a virtual approach avoids this. Okay, so somehow the data is always fresh. Also, one can use, since the data is in the sources, one can use existing data infrastructure and expertise to maintain these sources that often are already available. And in fact, often the data sources need to stay in large organizations. Why? Because there are many applications running over these sources already, and you cannot just simply throw away that because there is a complex infrastructure that runs on them. Okay, so they have to be maintained anyway. And the virtual approach also is better suited to deal with incrementality, in the sense that if you want to add additional data sources, you can just add them to your architecture. You define the mappings in a declarative way, and they are automatically incorporated in your integration system. So the next query that you issue will take into account these new sources. The same when sources change or when they get offline. So this automatically accounts for that. Now, let me make here also a disclaimer. This is ideally an ideal world in which you can always access the sources in a virtual way. In reality, we have seen that it's not always the case. It doesn't work always for various reasons. One is performance issues. Clearly, accessing sources in a virtual way has a cost in terms of performance because this data needs to be processed on the fly. And sometimes this processing might be complex. And there are also other issues related to quality of the data. So often the data sources are not of high quality. The data is dirty, as we say, so it needs to be cleaned. And there are many operations that you can do about cleaning the data that can be done on the fly, so in a virtual setting. But this is not always possible. Sometimes these cleaning operations are costly, and you want to do them once and then maybe store the clean data. So in general, the real setting that one has to consider is one in which you have a hybrid architecture, in which possibly part of the data is materialized, maybe the one that is very static, doesn't change very often, or that requires heavy cleaning operations. So you materialize that data and store it maybe in an additional source. But then data that is very dynamic, that one you keep virtual. So in general, you have to combine these two aspects. And this is in general a challenge also in terms of deciding, taking decisions about which data to materialize, which data to virtualize, and how to get a combined architecture. But in part, this is also supported by these data federation tools that I was mentioning before, which provide some partial support for materialization. So in part, you can also deal with it at that level. Okay. I will not talk about this anymore today. So I assume that we are dealing with a purely virtual architecture for simplicity here. Okay, so this was a brief motivation for what I'm going to talk about. And so this covered essentially the first bullet here, the challenges that we have in data access and what is the plan for addressing them. And now I want to go a bit more into detail about the various points. So I will talk about the various elements of this virtual knowledge graph architecture. And then I want to spend some time on 2 points. One is how to process queries and how to optimize the query processing. Okay, so this is a complex engineering activity to some degree, but there are some interesting aspects on that side as well. And I want to give you some ideas about that. The second point that I want to mention is related to what you were asking before. You were saying the ontology, how do we get that ontology? That's one problem. But I would say the even bigger problem is how to get the mappings. Because ontologies are available, mappings typically are not available. They depend on the specific sources, and they can also be highly complex. If you have tables with thousands, so if you have a database with thousands of tables and hundreds of attributes, and you need to map your ontology to these tables, you can imagine that the mapping itself will be quite complex. So coming up with these mappings is a challenging task and requires effort. So it requires investment, it requires also supporting technology. So I will give you some ideas of what we are doing in this respect regarding this problem here. Any questions? Yes?
So I assume that this relational database that company, I mean, they spent a lot of time like developing it and fine-tuning it and so on. So this information, this effort that went into the creation of this relational schema, is it something that we want to preserve, or like, you know?
To some degree, a database is actually a quite dynamic database in terms, it's a database that is growing. What is the idea of this database? It works, I mean, why does it have so many tables? Essentially, the way s.r.l operates is whenever they have a new drilling, they set up a new set of tables related to that specific drilling, where they store all the information regarding that drilling. Often these tables are very similar, I mean, but they're not always the same. It's not exactly the same table as before, because maybe they are using new drilling equipment, they drill in different kind of stratigraphic zones that require to keep different parameters. So they essentially, their choice is to create a new set of tables whenever they have a new drilling that they do. And then these poor data management experts, they need to look into this and take this into account when they receive these requests and try to understand whether now these new tables need to be incorporated or not in the answers that they give to their engineers. Now, in a setting where we are using this approach, a declarative approach, the idea is that whenever these new tables are added, essentially we understand their structure, also relying on similar tables that were already mapped in that database to the ontology. The ontology typically doesn't change much because the domain is always the same. And we define new mappings to these new tables, okay, taking into account the expertise or the experience that has already been done with previous tables. Okay. The mappings, I mean, I will say something about this. So we are working on automatic mapping generation, and there is some form of automation in that process, but it will not work to do it completely automatically. In general, it requires manual intervention and manual expertise. Although there is a lot one can do automatically, and that's one of the directions which we are working. Not only we, but there's a community also working on this automatic mapping, extraction, and generation. But it's a challenging problem. Other questions? Okay, then let me say something about the general approach to virtual knowledge graphs. And I want to say a few words because I'm not sure who is familiar with the various technologies. So I want to say a few words about the data model that we use for the knowledge graph, which is RDF, and the corresponding schema formalism, which is RDFS. Then the ontology language, which is OUL2QL. Carsten this morning mentioned OUL2EL. He said that OUL2EL is one of these sub-languages of an expressive ontology language, the OUL2 language. OUL2QL is another sub-language. Technically, they are called profiles in the W3C jargon, but a profile is essentially a syntactic restriction of a more expressive language. And OUL2QL is such a profile that is suited to this setting of ontology-based data management. I will say some words about SPARQL, the query language, which is somehow connected to conjunctive queries that were extensively discussed today by Carsten, but also in other talks in the previous days. And then I will spend a bit more time on the mappings, and I will give then how this framework can be formalized, and we'll say something about query answering in general, and then come back to this in the further parts, okay? So who of you is familiar with RDF and knows about semantic web? Just to understand, okay? Quite a few, maybe 1/3 knows something about this, okay? If you're bored, tell me. I will not go, I mean, will not say deep things about this, just to fix the terminology. One point that I want to make before I start with this is that we are clearly in a setting of incomplete information. So we are not in a pure database setting here. We're in a setting, an ontology setting. Why? Because the incompleteness comes on the one hand, because we are dealing with data integration. Data integration is inherently a problem where you have incompleteness, because in general, you cannot assume that your sources are complete with respect to the information that you want to see at the global schema, okay? That's one source of incompleteness. And this is essentially encoded in the semantics of the mappings. So these mappings are typically what are called sound mappings. So they correspond logically to implications, which means you could have at the global level additional data with respect to the one that is retrieved from the sources, precisely because the sources are assumed to be incomplete. And then another form of incompleteness comes from the ontology itself. It's a logical tier, an ontology, so it introduces incompleteness. However, since it is a logical theory, an ontology, it's suited, it's designed to deal with incompleteness. So that's inherent in the approach to deal with incompleteness. That's the plus. The minus is that dealing with incompleteness is in general something costly. We don't have a model, one database over which we answer queries. We have a set of models. In general, it's an infinite set of models. Each of these models could be infinite. Okay, so we have the issues that also Carsten was mentioning this morning, also in this setting, and we need to do in general logical inference. So the challenge is how can we get rid of logical inference and go back to a setting which we can use commercial technology for database, and that's exactly what we do in this setting. Okay. Now I want to talk about these various components of this VKG framework, and now these have been essentially the corresponding standards have been defined now since many years. You see that the dates, it's quite old, it's ancient times in terms of computer science. But these are the reference standards of the technology that we're using. That's semantic web technology. Specifically, RDF is a recommendation. In W3C terms, a recommendation is a standard. Okay, what is a recommendation is essentially a standard document to which people adhere and tools adhere. So RDF was defined in the current version 2014. The ontology language is this R2QN language, which was defined in its second edition. R2 is a successor language of the old language, which was called OWL. Now we call it OWL1, but it's now also 10 years old. The mapping language, the standard one is R2RML, and in fact, the technology and the tools adhere to this mapping language. I will not really present R2RML. I will present why, because R2RML is unreadable by humans. It's not meant to be read by humans, so it's meant to be read by machines. So I will not introduce it. I will just talk about a simpler to read language that is essentially equivalent, as far as we are concerned, to R2RML. And then I will say some words about SPARQL, which is the query language used in this setting. Let me also again here make a disclaimer. SPARQL is, and this technology is the one of the semantic web. Now, not all, let's say, industries, organizations who are facing these problems that we are talking about really embrace the semantic web approach and the semantic web technologies. So in fact, it now becomes also important to rephrase and somehow develop some of these technologies and tools in a more, quote, traditional setting. But still, I think the flexibility given by graphs is important. So we don't want to, at least in the general setting, to go to a relational approach, although in some cases, relational approach is also needed. So one direction which to go is to use property graphs. And then also rely on some graph database technology at various levels in this setting. One way is, for example, to provide let's say, a vision of such a system in terms of a graph database instead of a knowledge graph. Okay, so to present the data that is extracted virtually from the ontology in terms of a property graph, for example. That's one approach in which one can go. Another possibility is also to consider instead at a lower level graph databases as data sources, and possibly then exploit also the additional features and capabilities that these graph databases have with respect to more traditional relational technology. For example, processing path queries in an efficient way, which is something important. So these are all directions in which this kind of technology is also being explored and developed. But I will not really talk about this today. There's no time to talk about this. Okay, let me just say a few words about RDF. What is RDF? RDF is a language that is essentially a graph, a way to represent graphs. It's a graph-based data model where we have labeled nodes that are connected by labeled edges. And the nodes have three different forms. They are either literals, which denote constant values that belong to some data type. And they have, in RDF, we have the standard data type strings, integers, real numbers, and so on, those that you can imagine. Then we have nodes that are essentially identifiers. They denote a resource. They are called IRIS, for internationalized resource identifier. And these are just global identifiers on the web. Okay? An IRIS is, think of an IRIS similar to an URL, but it's not for a website. It's in general for a resource that is available on the web. And so they act as global identifiers. And then we have also blank nodes, which represent anonymous objects. You can think of them as existentially quantified individuals, as essentially quantified objects. The properties, which are the binary edges, they are also themselves denoted by an IRIS. So an IRIS might also denote a property, an edge between two nodes, okay, between two IRIS themselves. Okay, so this is just the general RDF model. Now, RDF is a graph, so you represent the graphs in RDF, and how do you represent graphs? As sets of triples, and you can just imagine each of these triples as two nodes with the connecting edge. So, and the three elements of such a triple are called subject, predicate, object. So the subject and the object are the two nodes, and the predicate is the edge that connects them. And here you see an example where you have a node that represents a certain person that probably lives in Bolzano. The name of this person is meant to be John, and in fact there is a property which is defined, by the way, by a standard ontology, the friend of a friend ontology, which you can find on the web, that defines this name property. And here we are stating through this triple that individual has the name John, and that's the On the right, you see this is the notation for a string, how to denote, how to associate a data type to a literal. Okay, John is a string literal, and we are saying it's of data type string. That's the syntax of RDF triples. Yeah, and here we have the 3 elements. I was saying there's some the standard allows you to write these iris in a more compact way by introducing abbreviations. You can introduce so-called prefixes. For example, you could say that friend of a friend, you want to introduce the friend of a friend prefix, so that when you want to denote this property name, you don't need to write the long IRI, but you just use the abbreviation that you have introduced this prefix, and then this becomes part of the RDF document that maintains the information, and so you can write your triples in a more compact way. You can also have other prefixes, for example, here, or you can also define a base according to which then you represent all your triples in your graph. Okay, but it's not really important. I mean, you could also skip this. Let me just give you a few examples. I was saying that the triple in general represents an edge between 2 objects, but there are also triples that in fact represent the membership of an object to a class, and these are the triples who have the special predicate RDF type. So, for example, you're saying that this IRI here, this person 25 belongs to the class professor. That's the way in which it is written. Now, I also use the more classical logical notation, which this is just a unary fact, okay, a fact of a unary predicate, the class professor, and you're saying that the P25 is an instance of this class. Okay, this is what you're more familiar with, probably. Now, let me just say that there is also an abbreviation. Since RDF type is so common, the typical abbreviation is E. So E stands for RDF type. Then we have a triple in the sense that I was saying before, as an edge. In this case, it's an edge connecting an IRI, an object, to a literal, a string, the string Artale. So I'm saying that the last name of this person is Artale. Again, I can write this as a binary predicate last name, which in this case would be a predicate that represents a so-called data property. So it connects an object to a data value. And finally, we have an edge that connects 2 objects. For example, here we are saying that this person P25 teaches the course C7. Okay? And where teaches now is a so-called object property, which connects 2 objects. We have an object for a person and here an object for a course. Again, we can write this in a more abstract notation as a fact, as a binary fact, where teach is a binary predicate. Now we can represent this set of triples as a graph. So here you see this representation of the triples, of some of these triples as this graph. So each of these edges represents one of these triples. I've put here a few of the triples here. I mean, these are not all. And for example, we are saying here that P25 is of type professor. So you see here in this graph, we have nodes that represent both objects. So that iris that denote proper objects, but also the classes themselves. Here, professor is meant to be a class, but this also becomes an object in this graph. Okay, it has its own IRI. And I'm saying that P25 is a professor whose last name is Artale and teaches this course here, whose title is KR, and so on. Okay, so we can represent such a set of triples graphically as the way you see here, and that's convenient when we will be talking about query answering, because query answering is based for SPARQL is based on graph matching, and so we need to have this graph representation of our data. Now in RDF there are also other elements. I mentioned data types. I could show you a list of the various data types. There are these blank nodes that I mentioned before, and also there is a mechanism to essentially group parts of a graph together. They are called named graphs, which lead to what are called quadruples. So the thing is more complicated than I've shown here, but we don't need to be concerned about this. Okay? This was the first part. I wanted to say now something about this R2QL ontology language. Now, just a few slides to keep it light that show you what is an ontology. An ontology is a collection of classes. So a key element of ontology is to group information in terms of classes that are organized in a hierarchy. Okay, here you have a nice hierarchy of ice creams. With this heat, you can enjoy it. But in general, in ontologies, as we have seen also today in Carsten's presentation, we have not only the classes, but we also have the properties. So the hierarchical structure is not only it's not the only aspect. We have the properties that can then be graphically represented, the whole ontology typically as a graph. So it's convenient to represent ontologies in the form of a graph. But for us, ontologies are not really graphs, they are logical theories. So I could write an ontology in terms of a first order logic theory. That's what you see here. I will use this as a running example for when we talk also about the mapping. So I have here the domain of actors and movies. Okay, so here you see an ontology that encodes the fact that in first order logic, every actor is a staff member, a series actor is an actor, a movie actor is an actor, series and actors and movie actors are disjoint, and so on. So I can write first order logic axioms that encode some knowledge. Okay. Now, in general, ontologies are not, we don't express arbitrary first order axioms in an ontology. We restrict the language because of computational aspects, because we want decidability of inference, decidability of query answering, and not only decidability, we want to do this also efficiently. So in particular, we consider ontologies encoded in description logics. And what you see here is the same ontology that was encoded as first order logic axioms now in the form of axioms in a description logic, and specifically these are axioms in a description logic that corresponds to this R2QL language that I will be talking about. So these are axioms in this DL-lite description logic. Actually, it's not really even precisely R2QL because we can also assert functionality in a logic. So this goes beyond this R2QL language, but it's something that has also been considered in description logic, and that is to some degree harmless, although one has to pay attention in how these various elements interact, obviously, as Carsten has shown today, quite much more detail than I'm doing now. But essentially, these actions that you see here express the same information that was before expressed as first order logic statements. I will talk about this language in a second, okay? Sure.
Usually get rid of it. So people in real life.
Yeah, okay. So it depends what you're doing. So now this setting is one in which we intend to capture conceptual models. So, and we will see this R2QL language has been designed and was meant to capture conceptual models. Why? Because that's what people use when they design information systems. And that's some formalisms they're familiar with and they can understand. Now, in conceptual modeling, functionality is an important feature because it's used to characterize better your domain. So, for example, your use case so it was not there because it was meant to be an R2QL ontology, the version that we are using, and R2QL doesn't support functionality. I will say something about this. Now, the question is, what do you do with this functionality? Functionality becomes important when you want to check consistency of your data with respect to your ontology, at least in the setting of this DL-lite framework. So functionality instead does not play a role in query answering. So once you have assessed that your data is consistent and that, for example, no person has two social security numbers or no well-bore has two different depths or whatever, which could be expressed through functionality, once you have assessed that your data is consistent, you can forget about functionality for query answering.
My question was whether you encounter.
Yes, in practice.
Where you needed something more expressive than that.
Sure, obviously, and not only functionality. I mean, in general, you need, so people, if you give them the power to use second order logic, they will use second order logic, provided they understand it. So this is always the case. But then it's an engineering task to agree between the ontology engineer who knows the formalisms and who knows somehow the pros and cons of adding more knowledge, and the domain expert who would like to have the maximum expressivity to agree on something that is manageable. Okay, so in the end, it's an engineering task, the ontology that you produce and that you use then in your integration system, for example. So as I was saying before, this R2QL language is one of the three profiles. There's also a third one, R2RL. apart in addition to OL2EL mentioned by Karsten. And OL2QL is derived from this DLite description logic family. So DLite R specifically is the logic that corresponds to OL2QL, and this belongs to this family of lightweight description logics. Why lightweight? Because they have a controlled expressive power, in the sense that you control exactly what you can express in this logic. It has been tuned towards capturing conceptual modeling formalisms, but keeping inference efficient. And when we talk here about efficiency, the key aspect was efficiency in data complexity. And in particular, in this setting, the data complexity is AC0, which is the complexity of evaluating first-order queries. And in fact, we have this first-order rewritability property, which means that queries over such an ontology, conjunctive queries or union of conjunctive queries, can be rewritten into first-order queries. Variants, in general, we rewrite them into union of conjunctive queries, and then these queries can just be evaluated, providing the implied answers. Okay, and this gives this AC0 data complexity, because the rewriting does not require to access the data. It's just a pure rewriting that uses only the ontology and the query, so it's not affected by the data itself. And then once one has the rewriting, one can just evaluate it over the data source, and this gives this is done with the complexity of first-order query evaluation, which is AC0. Okay, and in fact, also consistency can be checked in the same way. So the problem of, for example, checking consistency with respect to functionality that you might want to have in your ontology can also be reduced to a problem of query evaluation. And so in that sense, although our OL2QL does not have functionality, it can in fact be added to this framework, and for the purpose of checking consistency of the data with respect to functionality constraints. Questions? Okay, let me just skip this. I was mentioning that ontology has classes, data properties, and object properties. I was giving some examples in this running example that I will use. Also, I will use a graphical notation that I'm introducing in just one example. Now, in an ontology, in general, we have two parts. This was also mentioned before. We have what we call the ontology of T-box. Now, there's also ambiguity now in the terms here. Sorry for the confusion. Also because the terminology that I'm using here is not the OL2 or the OL terminology. So in OL, an ontology comprises, as you were saying, the T-box plus the A-box. So the intentional part plus the extensional part. Instead, I use for this the term knowledge base. So for me, a knowledge base contains what I call the ontology, which is the schema level information, so the axioms, plus the extensional part that for us is an RDF graph. Okay, so I call it RDF graph and not A-box because we are in the semantic web setting. Okay, so I use the term knowledge base for the combination of these two parts. Why? Because when we talk about ontology in the ontology-based data access setting, what we mean is just the intentional part, so the schema level information, which is made up of the vocabulary that is relevant for the domain, plus the axioms that capture the domain knowledge. Okay, and the RDF graph is just a set of triples, as we have seen before. So we have triples that an individual belongs to a class with this RDF type, and then triples that assert that an object has a certain data property, or that an object is connected to another object via an object property that we have here. Okay. Now, what are the axioms that we have in this OL2QL language? They are listed here on this slide. So this slide tells you what OL2QL is. And we can explain OL2QL quite well in terms of database terms. Okay, for those, where's Floris? Floris, you don't like description logics, right? And you never, so you can read the DLite not as a description logic, but just using your deep knowledge about databases. Okay, so what you have here, you have a class, you can declare a class. What is a class? It's a unary predicate. You can declare a property, which is a binary predicate. We have only unary and binary predicates. And in fact, we have object and data properties, so they are distinguished there, but semantically they are just binary predicates. Okay, and in an OWL file you have these declarations. You need to declare these terms that you want to use. Then you can assert that a class is a subclass of another one. That's just an inclusion between unary relations in database terms. Okay, because the class is a unary relation, so you say that the unary relation movie actor is included in the actor relation. You can also say disjointness. You can assert disjointness between two classes. That's a disjointness constraint, which could be a denial, can be written as a denial constraint involving unary predicates. You can say that a certain class is the domain of a property. That's again, it's the inclusion of a unary relation, so of the first component of a binary relation in a unary relation. Okay, that's what you say when the domain of a binary relation is a certain class. Okay, you say that the first component of the acts in relation is a movie actor. Okay, and you can say that a certain class is the range of a binary relation. And this is written in this way, but it just can be read by saying the second component of the X in relation is included in the movie relation. Okay, it's just an inclusion dependency between unary relations. You can also express something a bit slightly more complex. I'll skip this. I skip the, let's say, I skip the OWL notation. Here you saw the OWL notation because OWL is written in such a way that this requires a few lines to write. It's not very elegant in that sense, but that's how OWL is made. Instead, we can easily write it in this abstract DLite notation by just saying that the class movie actor, so the unary relation, is included in the first component of the binary relation. Okay, so that's again an inclusion dependency, and since you have here a binary relation on the right-hand side, this implies an existential quantification. So you need to existentially quantify the second component of the relation. Okay, which you also have if you just include a unary relation in a binary one. Okay, this can all be understood in database terms. You have also direct inclusion between binary relations. So acts in is a binary, it's a property, so it's a binary relation. Plays in is also a binary relation. So acts in is a sub-relation of plays in. That's a binary inclusion dependency. And we can also we have also inverse properties. So we can say that the binary relation is included in the inverse of another binary relation, which just means in terms of inclusion dependency, you swap the two components if you write it as an inclusion dependency. So this allows this logic to not give a preference to any of the two directions of a binary relation, because you have the inverse operator and you can always invert a relation and treat it, both components in a symmetric way. Okay. Any questions about this? So this is essentially what you can express in this DLite logic. So it's a pretty simple logic. And okay, here I have also some examples, and I give the semantics. So that's the semantics given in first order logic, but it's just what I told you in words. Okay. Okay, let me skip this for the moment. This is related to what I was saying before about the impact of disjointness or functionality, and also disjointness has a similar role as I was saying before. Disjointness is not used for query answering. It's just used for consistency checking of the data with respect to the ontology. Okay. The only axioms that are used for query answering are somehow the positive ones, those that do not involve this negation here. Disjointness, okay, I haven't put here disjointness of properties, which can also be asserted. So we have only disjointness here of classes, but this will not play a role in query answering. Now, I was saying that this logic is tightly related to conceptual models, and this is essentially shown here on this example, which for which I'm using here an ad hoc notation for the ontology, but this resembles, in fact, the UML class diagrams. I could also have drawn here an entity relationship diagram if you prefer. From that point of view, if you take this conceptual view, these formalisms are essentially equivalent. And what I can express in this DLite logic or OWL2QL, if you want, is essentially what I can express in such UML class diagrams about the domain. Okay, I can say that, and you see it here, I can say that classes are subclasses of other classes. I can say disjointness in such a hierarchy. I can talk about domain and range of binary relations. I can say that plays in has as domain actor and as range play. I can assert not only subclasses, but also subproperties. So the binary relation acts in is a subrelation of the plays in relation. And I can then do similar things for the data properties, which are just attributes in UML class diagrams. So for example, title is an attribute of this play class that has as range a string. So the title of a play is a string. And that's it. And also, sorry, and I also have here the mandatory participation. So I say that every movie actor must act in some movie, in at least one movie. Okay, so this is the kind of knowledge that we can express in this L2QL language. And in fact, it's convenient to visualize L2QL ontologies as UML class diagrams, for example, or if you prefer using such a graphical notation, but there's not much of a difference, as you can see. Okay. And these are exactly the constructs that are common in conceptual modeling. And that's why somehow this logic has been tailored towards capturing conceptual models. A few words about SPARQL. Now, we are in a setting of incomplete information. So a priori, we have to think well about what language we want to use. Now, in principle, we could go towards two extremes. Something quite expressive, SQL, okay, the language used in databases, or something much less expressive. So an ontology language, use the ontology language as a query language. Now, the first approach is the one that has been pursued in knowledge representation quite a lot. So in knowledge representation, before query answering became popular, people were considering the ontology language also as the way to query their knowledge. Okay, this is not very a good approach, because ontology language are good for representing knowledge, but they are not good for querying knowledge. They are way too weak to query knowledge because they don't have join capabilities in this ontology language. You have a very limited way to express joins, which make them unsuitable as query languages. On the other hand, if you use SQL, which is first order logic, at least first order logic, then we have aggregation and so on. If you use SQL, then in a setting of incomplete information, query answering becomes undecidable. So that's also not a suitable language. The negation is a problem here. So the idea is, the approach to follow here is to go towards something in the middle, which is conjunctive queries. And in fact, conjunctive queries have been initially studied in this setting, and then moving the whole approach to the semantic web framework, SPARQL was considered, has been studied as the query language. But the core SPARQL is very similar to conjunctive query. Then SPARQL has some differences. I will discuss them briefly. But essentially, that's the form of query language. And also then we can use not only conjunctive queries, but also unions, clearly. And in fact, one can use SPARQL just as a syntax for conjunctive queries, but in the end, there are differences. And I'll just point this out in a second. Now, what is SPARQL as a query language? SPARQL, it's the standard query language for querying RDF data. Now, SPARQL is based on graph matching. So a SPARQL, the basic form of a SPARQL query is such a graph pattern. So you have triple patterns and that are composed together into a graph pattern. So you can represent such a SPARQL query, such a basic SPARQL query as a graph. And you see here the representation of this SPARQL query as a graph, where you introduce nodes for the variables and also nodes for the constants, which in this case are both proper constants, but also class names are viewed as elements in this graph, as nodes in this graph with an iris, so this somehow they play the role of a constant. But since the predicate type, this actually represents a unary predicate. So you're saying that the object that will be instantiated by P is an instance of the class professor. And similar, the object which C is instantiated will be an instance of the class course. And then you say that the professor teaches a course, and the course has a title that is represented by T. Okay, so this is just a graph that represents the query structure. In addition, so this is just the basic form. In addition, we have several then other operators that make SPARQL actually a more powerful language. There is union. There is an operator optional. We say some words about this. Then there are complex filter conditions, which can be considered similar to selection conditions in in a conjunctive query. And then we have also aggregation operators. There is also forms of negation. And then, in fact, in SPARQL 1.1, which is the current version, we have also regular expressions, so-called property paths that allow to express navigation using transitive closure. Okay, so SPARQL has these features as well. Now, let me just say a few words about, okay, this is the simple form, these basic graph patterns that I already mentioned. It's a bit slow. And we can now evaluate such a query with a basic graph pattern over an RDF graph by just using graph matching. So we match the graph of the query with the graph of the RDF data, and the nodes that to which we match the variables that appear in the query head in the select clause of our query. Those represent the answer that we provide. So the answer is a list. Sorry, not a list. It's a set of instantiations of the answer variables. For example, here we see that these 4 answer variables are instantiated. Can be instantiated in 2 ways by matching this basic graph pattern in 2 different ways over the graph that you see here, and this gives us 2 answer quadruples in this case because we have 4 answer variables. Okay. Okay, this I don't think it's so important. It's just I think I'm using this somewhere on the when I have a basic graph pattern made up of several triples, they are all terminated by a dot. I can also group them together and write them in a bit more compact way by avoiding to repeat the first component of the triple if I put here a semicolon instead of a dot. This is just syntax. I mean, it's just syntactic sugar. What is more important is that I can obviously do also projection in SPARQL, so I do not need to put all the variables that appear in the graph pattern in the select clause, and those variables that do not appear, they are projected out. So in this case, I want only to return the last name and the title, the last name of the person who teaches some course together with the title of the course. I'm not interested in the IRI of the course itself. So this is just projection. And why I'm mentioning this? Because regarding this, there is a difference between conjunctive queries and SPARQL queries in their semantics that becomes relevant when we deal with ontologies. Now, we have here just a very simple correspondence between the SPARQL query and the corresponding conjunctive query by just viewing each triple. If the triple is RDF type, this becomes a unary predicate. I don't have one here. But if the triple is another one that uses just a data or object property, this just becomes a binary predicate. So we have here 3 triples that corresponds to 3 atoms in the body of my conjunctive query. And the variables that are in the select clause are the answer variables of my query. Okay, so it's an immediate correspondence. You don't need to say what a conjunctive query. If I have a projection, then I will have in the head of the query only a subset of the variables. Okay. So again, I have this correspondence between SPARQL and conjunctive queries. Now, there is, however, a difference when we come to the semantics of SPARQL and conjunctive queries in the presence of an ontology. Why? Because in SPARQL, all the variables that appear in the body, they require to be instantiated on nodes of my RDF graph. Okay. Also those that are projected out. So here, for example, I'm projecting out the P variable. Still, in order to find a match for this query on the graph, I need to match this P variable on some node of the graph. Now, if I just have an RDF graph, there is no difference between the conjunctive query and the SPARQL. The difference comes if I have an ontology, because if I have an ontology, this ontology might imply existentially certain nodes. So certain nodes might not be present in the graph, but they are existentially implied. Now, if I have such nodes that are existentially implied, and I evaluate this conjunctive query over my graph, then the existentially quantified variable in the conjunctive query, in this case, this one, can also match these existentially implied objects. So, whereas in SPARQL, this is not the case. So all the variables, including those that are appear just in the body and not in the head, need to match some node in the graph. Okay, so this creates a difference in the evaluation of SPARQL queries and conjunctive queries in the presence of ontology. And this is quite relevant because practically this means that the evaluation of SPARQL queries is simpler than the evaluation of conjunctive queries over knowledge graphs or RDF graphs in the presence of an ontology. Okay. Yes. Yes, but so if yes, I will say something about this later. But if you now reformulate SPARQL queries according to the so-called OUL2QL entailment regime, which means take into account the reasoning that is done over the OUL2QL ontology, you need to take into account this difference. So the existentially quantified verbs in the SPARQL, so the verbs that appear just in the body of the SPARQL query, they need to match nodes that you have explicitly in your graph, in the RDF graph. And so if you use a reformulation algorithm for conjunctive queries, you will get the answer according to the semantics of conjunctive queries, which is not the same semantics as SPARQL. So this means you need to adapt the reformulation algorithm to take into account the SPARQL semantics. It's not the same reformulation as you have for conjunctive queries. In fact, it's simpler because you don't need to do this form of existential reasoning, essentially. And if you talk to more applied people, in fact, they say this existential reasoning is useless, okay? And they are advocating to actually switch it off because it just causes additional overhead. And they say that anyway, users don't really understand this existential reasoning, they don't count on it, and one should just switch it off. This is the practical attitude. I always have discussions with Benjamin, who is the CTO of Ontopic, about this aspect, but the experience is that in practice, people don't want this. Sorry, no, it's not exactly. No, the ontology. So the part of the ontology that causes existentially quantified objects to be considered, that part is not needed according to what counts in the ontology is the reason with respect to the hierarchies. But that, as we will see later, can be done. So reason with respect to the hierarchies can be done in a more efficient way by, in the context of mappings, we'll talk about this, by this so-called mapping saturation process that we'll mention later. Okay, so this can be dealt with in a more efficient way. And then if one switches off this reason with respect to axioms that have an existential quantifier, yeah, yes and no, but data log is not AC0. I mean, if you have a data log, it depends what you want to use of data log. Yes, yeah. Yeah, okay. This was illustrating this difference. Okay, but I think I mean you can look it up later on the slides. It's what I just explained here on the in terms. It's just working with the models of the ontology, where you have here an existential axiom that implies an object that allows you to answer this SPARQL query using existential reasoning. So this is a simple example that shows the difference between the SPARQL semantics and.
But if you switch that off, you may lose also entailments over reactive domain. Because I may derive something, I don't know, class C of A, but this C of A is derived because of an atom that has an anomaly.
It depends. I mean, you don't. So you saturate the mapping. So you take into account all the reasoning with respect. No, yeah, but yes, I agree with you. But that's the discussion I have. I mean, I agree with you. But the argument by the practitioners is that this information that you lose, these answers that you lose, are not really relevant because users anyway don't count on them. That's But I mean, I take your view. I mean, if you switch it off, you lose. So your answers are incomplete with respect to the semantics of conjunctive. But be careful because SPARQL has a different semantic. So in fact, in SPARQL, this is what you want to have, unless you write your queries using anonymous variables, which you also can do. I mean, one has to pay attention. I mean, in a SPARQL query, you can also have anonymous variables, which means you don't mention a variable explicitly, although you have there an existential implied variable. But that one cannot appear in a cycle, so it's only a tree-shaped query that you can express. And that one, that's where it makes a difference, right? But the argument is that this is practically not significant, what you lose there. Yeah. Yes, but this aspect, I will talk about this, how at least we propose to manage this, because this is tightly connected with how mappings are managed. And this is this exponential blow up in general can be avoided by using query optimizations that take into account the mappings, and by using other techniques, which I wanted to talk about. Actually, I don't know whether I will be able, because I'm very slow. I see. I started. No, I mean, okay. So you know it's ready for, yes, okay. I still have some time. Yes. I will come to this, but I agree with you and with Andreas that by switching it off, we might lose some answers. I'm not saying that switching it off gives you the same results. The other point I want to mention, I will not have time to go into the details about optional, but optional is another construct that is present in SPARQL that causes significant complications. In this case, SPARQL is more complicated than conjunctive queries because we don't really have optional in conjunctive queries. Now, what is optional? Optional allows you to match a part of the, so to obtain an answer and instantiation for a variable if there is a match. But if there's no match, you still obtain instantiation for the other parts of the variable. For example, in this case, we want to return a person together with the last name and also the first name if the first name is present in the graph. Okay. Now, for example, here we have that for Anna Rossi, we have the first name and the last name. So Anna Rossi is here, it's that object, okay, P38, who has a last name, but also a first name. So we'll return a match for all three variables. Instead, for Artale, we only have the last name, but we don't have a first name. Still, since we require, so since in the query, the first name, the instantiation for the first name is within an optional clause, we still return a match for the other variables that are outside of the optional, okay? So you can return partial matches. So you see in SPARQL, you don't really always return tuples that have the same arity as the number of answer variables, but in the case of optional, you might have some of the answer variables not instantiated. Okay? That's why, in fact, technically, the answer to a SPARQL query is a set of instantiations of the answer variable. It's not a set of tuples. Okay? So this optional intuitively corresponds to an outer join in SQL that you would have in a SQL query, okay? Because also in an outer join, you might have a null value. In SPARQL, you don't return a null value, you just miss a match for one of the answer variables. And I will not say anything more about optional, but optional complicates query answering substantially. And it requires, then, if you want to optimize queries, you need to take this into account experience. So there's work on optimizing also specifically with respect to the presence of optionals. Also because it has, the way it's defined, semantics defined, you have some form of negation due to the presence of optionals. Okay, so I just talked briefly about basic graph patterns and briefly about optional. I mentioned the other constructs that we have in SPARQL. I will not use this, so I didn't even introduce them. But obviously, if you want to consider SPARQL properly in this setting, you need to deal with all these constructs. And in particular, for example, the technology that we are developing, the on-top system that is developed in Bolzano, deals with all these constructs, except currently for path expressions, which are outside of the fragment that we support at the moment. But an important aspect is, for example, aggregations, goodbye operators and aggregation functions, which is a key aspect if you want to use this language in practical settings. Okay, now let me come instead to a key point, which is the mapping language. So how to map an ontology to a relational database. Now, the mapping is the component of this architecture that encodes how the data in the sources should be used to create the objects and the values that are present in this virtual knowledge graph that the user then virtually queries. Okay, so it tells us how to construct this virtual knowledge graph formulated in terms of the vocabulary of the ontology. Now, as we were saying, here's just a summary of what I was already saying. The queries are formulated over the virtual knowledge graph. So the queries are answered with respect to the ontology and the data of this virtual knowledge graph. But this is not materialized, it stays virtual. And intuitively, the mapping is then used to translate the queries over the ontology into queries over the data sources. That's how we use the mapping. We don't use it effectively to populate the knowledge graph. We use it to translate the queries. Okay. We define the semantics of the whole system in terms of the knowledge graph that is being generated through the mapping, but then the actual query answering process translates the queries. Now, one aspect that is also dealt with by this mapping is to deal with this so-called impedance mismatch. The fact that at the lower level, we have a database that stores values, so strings, numbers, integers, whereas at the upper level, we have an ontology that stores objects, so abstract objects that have an identifier. So we need to create these objects from the data in the sources, and that's what the mapping also does. So it is a way to specify how the object should be created at the level of the ontology from the values obtained from the sources. So this specification is embedded in the mapping. Now, how does this mapping look like? The mapping consists of a set of so-called mapping assertions. Each of these mapping assertions has a SQL query on the left-hand side. This is what we call the source part of the mapping, or the source query, which is just a SQL query. And it has a target part, and the target part is a set of so-called triple patterns. I will say in a second what this is. So these triple patterns are essentially atoms, and these atoms have as predicates the classes and properties of the ontology. And they make use of the answer variables of the SQL query. That's why here I use this X. X are the answer variables of the SQL query. They appear in these triple patterns. And the triple patterns contain also this T that stands for terms that technically are called IRI templates. I will say a second on the next about. I will say something about this on the next slide. But intuitively, it's these IRI templates that tell us how to construct valid IRIs for RDF from the values in the database, essentially by concatenating the values coming from the database with among them and possibly also with string constants. Okay, so we construct an identifier through string concatenation intuitively. And yes, so when I use a variable of the source query, this is meant to be the answer variable of the SQL query. And the mechanism with which we construct these objects is the following. So the idea is that the answers that are returned by the SQL query, each tuple that is an answer of the SQL query is used, so the values that are returned by the SQL used in these IRI templates to construct the object identifiers. And specifically, what we have in these triple patterns, we have a set of triple patterns that have this form. They are either RDF type assertions, so asserting that an IRI that refers to some answer variables of the SQL query is of a certain class, so belongs to a certain class. So C is a class of the ontology, or that two IRIs that are constructed using the answer variables of the SQL query are connected by a certain property. So prop here is a a data or object property of the ontology. And the idea is that each answer tuple is returned by a source query when it is evaluated over the database. For each such answer variable, so for each such answer tuple, the ID template generates either an object or a value, depending on the form of this ID template. And this object or value populates the virtual knowledge graph and specifically populates the classes and properties according to what is specified in these templates. So this is a way to provide this solution to this impedance mismatch, to the fact that we have values in the database and we have objects in the ontology. Yeah?
You're emphasizing practical adequacy. This step is something that would worry me a bit more. I mean, you're not only changing schema now, you're also changing the data model. And in your OIL application, for example, you said your tables have like dozens or hundreds of attributes. I see with streaming numerical data. Now it gets transformed in some way to objects. That's a good thing, or we just mess up the data?
No, this is all related to how you do this transformation. And this is related to what I will be talking about how to design these mappings. And there are specific patterns, and I will talk specifically about mapping patterns that occur frequently when you do these mappings, okay? So there are specific forms that are related essentially to the keys that you have in your database and the foreign keys that you have in your database that tell you which are the values that you should use to generate these object identifiers. Let me just give you a simple example here. So I use now I don't use I told you, I don't use the R2RML language because it's unreadable. I use a much simpler language, which is equivalent in expressive power to R2RML, but it's much easier to read. It's the one that we have in our system. I was saying, when we have a mapping, we have the source part, which is a SQL query. So here I'm assuming to have a SQL query over a movie table. I will introduce this example in a second, where this movie table has some attributes, movie code and movie type, movie title and attribute type. So here I have simple SQL query. And then there is this target part, which is made up of these triple patterns. For example, these are two triple patterns that could appear in the target part of this mapping. And I have a second mapping that has a different source query and a different target part. In this case, I have only one triple pattern. Okay. Now, let me discuss this example. Okay. So let's assume we have this ontology, a very simple ontology, the one that we saw before about our movies and actors. And I'm also actually only using a part of this ontology. I'm only using the part that is actually referred to in the mapping, in the target part of the mapping, because I'm constructing instances of the class movie, of the class, let's see, the mapping of the class, of the class movie, of the title data property and the acts in object property. So the title is a data property or an attribute, if you want, of a play. Acts in connects movie actors to movie. Okay, so I want to populate a part of this ontology using these mappings. And where do I get the data to populate this ontology? I get it from two database tables. So I assume I have a movie table that stores, that has 4 columns, possibly additional ones, but here I'm interested only in these 4. It has a movie code, a movie title, a year, and the type of a movie. Actually, here I'm assuming the view that our kids have. For them, movies and series, they are somehow in the same category. So I have here actually both movies and series. So for example, The Matrix is a movie that was produced in 1999. Altered Carbon is a series in 2018, okay? And in this movie table, I have both movies and series and distinguish them by this type attribute. Plus then every movie has its code. Instead, in the actor code, I store the information about the name of the actors, a code associated to the actor, but I also store in which play the actor plays. Okay, here there is a code that tells me that Keanu Reeves plays in this movie, and Carrie Ann Moss plays in this other movie, and which is this movie? Actually, it's The Matrix, and Harrison Ford plays in Blade Runner. Okay, that's the intuition behind this table. Now you might say this is not a very good table because it's not normalized. You're right, it's not normalized, but I don't have the control over this table, right? So this is a table that someone has given me, I have to deal with it. That's where the information is that I want to access. I might not be able to modify this table, I can only query. Okay, that's the typical setting in which we are when we access legacy data sources, okay? And they're often badly designed. So for example, here they are not normalized. Now, what do I do here? I want to populate this ontology from this table, so I can define two mappings. The first one queries the movie table, just the movie table, okay? And in fact, here I'm interested in populating the movie class just with proper movies. So I want a query here, the movie table filtering according to the types. I only want those movies that have type N and not the series, okay? And I return the movie code and the movie title. And now what do I do with this? I use the movie code to create an object that is a movie object. And to create this object, I put a prefix that is a string, the string :m/, followed by the code of the movie. And now intuitively, this seems reasonable. Why? Because intuitively, I could imagine, although nobody's telling me this, that this movie code is a key in the movie table. So it's a reasonable way to create a movie object using the code, okay? And in fact, that's what I'm doing. And I put here a prefix to distinguish the movies, for example, from the actors. And what I do, I say that this movie belongs to the movie class, and I also say that this movie has a title that is the title obtained as an answer to this query. Okay, the movie title is here a string. This creates a literal, which is a string value that is obtained as the year, as the title here. Okay. So if I apply this mapping, sorry, if I apply this mapping intuitively, if I use this mapping to apply it to this table, and I issued the query and was creating the knowledge graph materialized, I would get the following triples in my knowledge graph. I would get that M5118 is an object in the class movie. Also, M2281 is an object in the class movie. Why? Because this is what is returned by this query, and this triple pattern asserts that these two objects belong to the class movie. And the first one has the title The Matrix, the second one has the title Blade Runner. Okay, so this creates this mapping applied to this table, creates these four triples that constitute part of my knowledge graph. If I was materializing this data, okay, this is just to understand the semantics of this mapping. And similarly here, I have here a query that is slightly more complicated. Why? Because here again, I want just the movies. So I want, what do I want here? I want to understand which actor acts in which movie. But since the information about whether this is a proper movie is contained in this table, I need to do a join between these two tables on the code. So I join P code of actor with M code of movie. That's what I do here. And then I select only those movies that have type M. And those I return this triple, putting the actor, so creating an actor object which now has a prefix A, and connecting it to the movie object through the actin property. Okay. And now if I apply this mapping to these two tables, what I get these three triples. Okay. I get that the actor 438, which is this one, acts in the movie 5118. 572, which intuitively is Carey and Moss, acts in the Matrix, and Harrison Ford intuitively acts in Blade Runner. Okay, so yes.
Can you comment on why the initial manipulation
do we have an implementation for source to target TGDs? So the point is. This mapping language is essentially the R2RML mapping language, right? Which has been defined in the W3C community. Now, what we have been doing, we are implementing, realizing this technology in the context of the semantic web technology stack, right? So in that technology stack, people expect to use ontologies in R2QL, they expect to use R2RML mappings, and they expect to obtain RDF data. Yes, sure.
I would argue that it's very bigger because you can use a lot of tools that have been developed for target. But maybe we can talk about this when we talk about the definition of the map.
Okay. But essentially, these are the definitions of the mappings. I've already told you about the definition.
Because there are many tools where you can define social target helping the user to discover the.
Okay, no, I would be curious to see this because, I mean, we are developing tools to do mapping design, and we have looked at commercial technology, but there's nothing that is really usable in a commercial setting, as far as I'm aware. But maybe we have missed something. So I would be interested to talk about this.
What is just a conjunctive query, right?
Sure.
Because you ask if there is an implementation, but why you need something better than just a conjunctive query?
No, but we don't have just conjunctive queries. I mean, in the source, we have SQL queries, right?
Okay, but then it's way more powerful than.
Yes, yeah, sorry, maybe I should have said this. Yes, sorry, I forgot. I mean, in fact, in the source, we don't want to, I mean, this is not realistic to restrict to conjunctive queries. Sorry, yeah, I was not very aware. Sorry? In general, you need, especially for the data cleaning operations, which are very frequent in this setting. So one of the key aspects of mappings is to clean the data. And there you need way beyond the conjunctive queries. Then, I mean, how much power you put in the target queries affects how much you can optimize your query processing. Because the expressive power, or the constructs that you use in the source part of your mappings heavily affects the kind of optimization that you can apply in query answering. So this is a crucial aspect in general, and one has to pay attention to this. So in principle, from a point of view of implementation, our tools allow you to write arbitrary SQL queries. But if you write arbitrary SQL queries, for example, with complex aggregation operations or complexly nested queries, the opportunities for optimizations are drastically reduced. And then you see this immediately because performance goes down. If your queries fall in fragments that we are able somehow to parse and for which we can apply optimization techniques, we are able to drastically simplify the generated queries. And this is crucial for practical applicability of the techniques. Yeah, but in general, one has to go beyond the conjunctive queries on the source part of the mapping. Okay. But also, from a point of view of defining the semantics, this is not really an issue. I mean, because you can have in principle an arbitrary computable query there in principle. Yes, let me, if I manage, okay. Yes, it's a good moment because my machine is again stuck and I cannot advance. So it's necessarily a good moment. In the meantime, I try to wake up the machine. Okay, we stopped here, showing how these mappings work. I mean, conceptually, it's very simple. There's nothing fancy about this. It's just a simple mechanism to extract data virtually and construct objects in a knowledge graph. I will say something later about mapping patterns that tell you how you choose what should be the attributes that you use to create your object identifiers to use in your iris to identify the object. So there are some common structures, and I want to say a few words about this later. I notice if you look at the number of slides there, you realize, as Carsten also was realizing with his slides, but I realizing even more dramatically that we will never finish the slides. So I will have to cut, but I had already foreseen to cut slides. It's not unforeseen. And I know roughly where to cut. Now, this is just about the standard mapping language. I told you about R2RML. There's not much more to say. Also, I don't want to spend too much time on formalizing all of this. Obviously, we can give semantics to all of this in terms of first order of ontologies, and the semantics is the one that you would expect. So we provide a formalization of such a system in terms of a triple, the ontology, the mapping, and the database schema. If we add the database, we get an instance, and then we can define the semantics in terms of the models of the corresponding ontology. And the models are defined intuitively by saying what are the objects that you have in your domain, the domain of the knowledge graph that you are constructing, that you're obtaining from the data through the mappings, as if you are materializing it. This gives you an A box in terms of description logic ontology, so the knowledge graph together with the ontology, which means the intentional component, you have then an ontology-based setting, and you answer queries over these ontology-based settings. That's the semantics, okay? And that's what, sorry, I'm going back. That's what we are saying here. And you compute then certain answers, which are just the logically implied answers in line with what Carsten was saying this morning. So there's nothing special about this. We have this notion of first-order rewritability. So the ontology language, this DL-Lite family, and specifically DL-Lite R or 2QL, has been designed in such a way that conjunctive queries and unions conjunctive queries are first-order rewritable, which means if you can rewrite a query over the ontology in a new query that, for example, can be a union of conjunctive queries, such that evaluating this rewritten query over the data gives you the certain answers to your original query over the ontology together with the data. And this gives you as complexity AC0 in data complexity. And then one can show that this logic is, for example, log space in the complexity in terms of the ontology and the mappings, and NP complete if we take combined complexity. But this is not surprising because already conjunctive queries over a database are NP complete. Although here the NP, I mean, practically there's a further component that contributes to the complexity, which is the exponential blow up that you get if you naively apply this rewriting and the technique to unfold your mappings that we will talk about in a moment. So I want instead to spend, I would say, half an hour on this optimization and half an hour on the last part, which is this designing the mappings. And I give you some ideas about how you choose what are the attributes that you use, for example, to identify the objects based on a pattern-based approach that helps practically in this setting. First, a few words about optimization. Now, conceptually, the query answering process is simple. You have a query over the ontology. You apply rewriting with respect to the ontology axioms. You get a rewritten query, which will be, for example, for a query that is a union of conjunctive query or a SPARQL query, you get a union of conjunctive queries over the ontology. Then you consider the mappings and you unfold your query with respect to the mappings. You get a SQL query. Now, this unfolding is not just view unfolding. I'll show some ideas behind this because you have to take into account these IRI templates, so which are essentially Skolem symbols that appear that you have to deal with in doing the unfolding. So the unfolding is in practice a partial evaluation of logic programs, if you want. But you get from that a SQL query that you evaluate over your database. You get your answers. Then you have to take into account the mapping again to translate this relational answer into a set of instantiations of the answer variables of your original SPARQL query. If we start from a SPARQL query, that is the answer that you provide to the user. So conceptually, it works like this. In practice, it doesn't really work like this. So if you do this in practice and you don't apply optimizations, the system will just not work. I mean, our first implementations of the system 10 years ago was implementing this from a simple query and not a too complex ontology and simple mappings. We got a query, a SQL query that had 100,000 unions, literally 100,000. And obviously this doesn't work. And why doesn't it work? Because there are exponential steps that blow up exponentially what you get as intermediate results. And if you don't apply optimizations in that setting, it doesn't work in practice. So let me just briefly talk about how, first illustrate the simple approach behind the query answering, and then I will discuss a few optimizations that one can do here. So the steps are those that I was mentioning before, plus there is an optimization step. But also this one is not really how it works in practice. Now, the first aspect is the rewriting step that I was mentioning. So rewriting your query with respect to the ontology. And now there are two aspects that one has to consider. One is the hierarchies of classes and properties. So essentially the implications that do not involve existential quantifiers. You just have subclass and subproperty assertions that have to be taken into account. And then there is also the part that involves instead axioms that have an existential on the right-hand side, which correspond to these participation constraints, if you want, in a conceptual model, or an inclusion dependency where on the left-hand side you have a unary relation, on the right-hand side you have a binary relation that implies an existential. Okay, so they are considered separately, and they have somehow they play a different role in the whole rewriting process. Now, very simple, if you have your axiom that says that every graduate student is a student, and you ask for, and you know that John is a graduate student, and your query asks for a student, in SPARQL it's written like this, obviously you should return as answer John because of the axiom that tells you that graduate student is also a student. And now how do you get this? Very simply by rewriting your query. Sorry, no, why don't I have the rewriting? Okay, this was just to illustrate the idea. I will show the rewriting in a second. Now, this is dealing with a hierarchy, okay? Instead, if you have an axiom that says that every student is supervised by a professor, and you know that John is a student, and your query is asking for, give me all those objects that are supervised by some professor, which in SPARQL you could write in this way using an anonymous variable, which I didn't explain. Then again, in this case, you would like John to be returned as an answer. Why? Because your ontology axioms implies that John is supervised by some professor, okay, being a student. So this involves existential reasoning, because in order to answer this query, somehow you need to know that there is a professor. Although you don't know who the professor is, clearly there will be some professor who supervises John, okay? And this is what we mean by existential reasoning. The query writing algorithm takes this into account. And for example, if you start from your query that asks for, give me all those x's that are supervised by some professor, you can use the two axioms that you have here, that students are supervised by professor and that graduate students are students, to rewrite this query into, first of all, take into account the first axiom into a query that returns students. And then once we return students, we also want to return graduate students because of this axiom. Intuitively, very simply, we apply the inclusions from left to right, or if you want, we chase the query with respect to the inclusions. And this chase terminates because you cannot generate an infinite number of different queries. So the query writing algorithm essentially does this. It chases the query, it writes your query, and this rewriting is finite intuitively because at least for this logic, every writing step does not increase the length of the right-hand side of your query, and you have only a finite number of different right-hand sides or different queries that you can generate. And this is what the rewriting algorithm does. Now, let me skip this aspect. This is related to the semantics. I mean, one can show this logic has a canonical model property. So we know that there is one model that is the representative of all the models over which you would like to answer your queries in such a way. So is the representative, it means that if you have, if your query maps to this canonical model, then it maps to all the other models. Why? Because there's a homomorphism from the canonical model to all the other models. Okay, and so in principle, you can answer your query just over the canonical model. This canonical model in general is infinite, but the rewriting algorithm essentially rewrites your query in such a way that there is a match of the original query over the canonical model, if and only if there is a match of the rewriting over the explicitly asserted part of your knowledge base, over the A box. Okay, that's the idea behind this. And the rewriting algorithm just implements this technique. Let me skip this. Let me also skip these steps. This was just illustrating the rewriting algorithm. I just want to show one slide where it's summarized, which is the one I wanted actually to use. It's this one that shows which are the rewriting steps that you apply. So very intuitively, if you have an atom in your query, you apply the inclusion axioms, the inclusion assertions in your ontology from right to left. So just for example, if you have a C2 atom in one of the conjuncts in your union of conjunctive query, and you have these inclusion axioms, you can rewrite this conjunct by just replacing the axiom, the atom corresponding to a class in the right-hand side of the axiom with the same atom, but where you have replaced the class with the one in the left-hand side. And similarly for the axioms that don't have existentials, for the axioms that have existential in the right, you need to pay attention on when you can apply this rewriting step. But the idea is very simple. You apply chase step of your query, or your rewriting step of your query, until you saturate, and this is the rewriting algorithm that saturates your query. And when you have obtained, when you've finished saturating your rewriting, that's the query that gives you the certain answers. Now, okay, let me skip all of this. Sorry, I should have just removed these slides. Now, simple observation shows that this in general leads to an exponential blowup. You can just show this by taking a query that has n atoms, C1 to Cn, and you have for each of these atoms, you have an axiom in the ontology. Sorry, this doesn't react very well. I don't know what the machine has, it's very slow. Okay. So if for each of the atoms in your query, you have an axiom in the ontology where that atom is in the right-hand side, then you can choose for each of the atoms whether to rewrite it or not. And for each of these choices, you have one union in the conjunctive query, which means that in the end, you have 2 to the n unions in the union of conjunctive query. So this means that in practice, this blows up exponentially, and sorry, in theory blows up exponentially. The problem is that this applies in practice as well, because it's not very uncommon to have similar situations. Okay? So this is not just a theoretical blow up. This is related to the 100,000 queries that we got in our first implementations. A similar situation occurs with the mappings. Now, let me just say a few words about this. I said, when I was describing the mappings, I said that we have in the source part a SQL query. In the target part, we have a set of triple patterns. Now, practically, it's difficult to deal with this set of triple patterns. So what we are doing, at least in our implementation, is we split this up. So we split up each mapping assertion that has a set of triple patterns into a set of mapping assertions that have all the same query on the left-hand side, the same SQL query, but a single atom in the right-hand side, because it's simpler to deal with such mappings that have a single triple pattern on the right-hand side. And this is what we call here the splitting. So for example, if you have here a mapping that populates has four triple patterns on the right-hand side, we get 4 mappings all with the same SQL query. Okay, but we don't forget that these mappings come from the same SQL query. Sorry, that these 4 mappings come from the same mapping and have therefore the same SQL query in the right-hand side. Okay, let me skip this because that's not what we are doing. We are not materializing. That's just conceptually to understand what is going on. Instead, what the algorithm does, it uses the mappings to unfold the query. So it essentially views the mappings as a kind of view definition and unfolds the query with respect to this view definition. Okay. So technically what we do, we introduce a view symbol for each mapping assertion, where we have before splitting. So for each query that we have on the left, for each SQL query that we have on the left-hand side, we introduce an auxiliary view symbol. And we introduce such a view definition where we define this auxiliary view symbol in terms of the SQL query. Then we look at the split version of the mapping assertions, and we introduce clauses that correspond to the split versions, where we view simply each mapping that you can read as an implication as if it was a corresponding clause, where the right-hand side, the target part of the mapping, is just the head of the clause, and the auxiliary symbol corresponding to the SQL query on the left is just the body of the clause. And then we have we can just view this as a set of clauses, and our query contains the atoms in its body that appear here in the head, and then we just have to find a most general unifier between the query and the heads of these clauses, and apply this most general unifier to obtain a new query formulated in terms of the auxiliary symbols. Let me just show this on an example. Here we have these two mappings, two SQL queries on 4 atoms on, no, sorry, here 4 and here 3 atoms, here triple patterns on the right-hand side. This gives rise to 7 split mapping assertions that refer to 2 auxiliary symbols corresponding to the 2 SQL queries, the first one and the second one. Here we have aux1 and aux2. And notice that what we have here in the heads of these mappings are the the ID templates that I have here written as if they were s.r.l functions, okay? Because mathematically they are s.r.l functions. So just use this notation because it's more compact instead of writing an ID template. Okay, but read this as an ID template that has this as a kind of prefix, and then has here the answer variable of the SQL query, because P code is one of the answer variables of the SQL query, and so on for the other ones. Okay, so we have here these ID templates or s.r.l terms in the head of our clauses, and now we need to, and if we now have a conjunctive query that refers to these ontology predicates. Actor is a class name, name is a data property, and so on. And we have here here are the relevant clauses that we have obtained from the mappings. We can now find the most general unifier between the body of our query and the heads of the various clauses that we have introduced. And this is, that you see here, is such a most general unifier. For example, the A variable is unified with act A code because it uses the same predicate symbol, and we can unify it, and so on. So this most general unifier, we can apply it to our query, and we obtain a new query now which we have now unified. So in which now all the atoms in the body now unify with the heads of the clauses, and we now substitute each atom with the corresponding body of the clause. If this advanced, it would be better. We get a new query in which now we make use of the auxiliary symbols in the body. And remember, these auxiliary symbols represent the SQL queries that we had in our mappings. Now, one thing that we see immediately here, I don't want to go into details, but we see here that the same symbol is repeated multiple times. Okay, so these are self-joins, and they are introduced by the mechanism of mapping unfolding. Okay, so we see here that we had only 2 mappings, but we had 7 atoms here. So the aux1 symbol is repeated 3 times, and the aux2 symbol is repeated 2 times. And we also see that, for example, the first argument here is the same. Okay, the play code here, aux2 is over the same play code. Okay, and this is relevant. Or here, aux1 has the same A code in the second component, for example. Okay, and this is an issue because this query is not the best that one could produce if one has additional information. For example, if we know that in our query the play code that is returned by this query is somehow a key of the tuples that are returned by this query, then we know that these 2 atoms can be replaced, can be unified by a single atom. So this query becomes equivalent to the one in which we replace the 2 atoms by a single atom, okay, and in which these underscores, which are anonymous variables, for example, the last one is unified with the matrix. Okay, so we can optimize this query exploiting the fact that the first component here is a key of the returned relation, if we have this information, obviously. But this is one opportunity for optimization. This one just shows that also in this step we have an exponential blow up. It's again a simple example analogous to the one of the rewriting, now just worked out with mappings, where for each atom in my query I have now two mappings that essentially can be used to unfold these atoms. And again here, choosing one or the other, I get an exponential number of different unfoldings. Okay, so we have an exponential blow up in the rewriting, a potential exponential blow up in the mappings. Again, this is not just theoretical, this occurs in practice because it's very common that for the same symbols in your ontology, you have multiple mappings that define the symbols. As soon as you have two sources that contain the same information, these two sources will be mapped to the same symbols. So this gives rise to two different ways to unfold your query that contains that symbol. Okay, and in practice this occurs. Okay, so again, we have this exponential blow up. Now, to take this into account, there are many ways to exploit this unfolding and do this unfolding in practice. So the one that I've shown you is just the one in which you simply unfold each atom separately. And so what you generate from a single conjunctive query, if you unfold each of the atoms in the body of your query with respect to the various mappings, and for each of these unfolding, you generate a new conjunctive query in a big union, you get this exponential blow up. But in practice, you might do it also differently. You might, instead of unfolding each atom separately, you could unfold an atom with a union, another atom with the other union, and then construct your query as a join of unions. Okay. Now, what is better? Which is the best? Which is the better unfolding and hence reformulation that you can produce? You could say, obviously, the better one is the one that computes a join of unions, because instead of being exponential, this join of union is just has the same size as the query. The problem is that this join of union, if you look at how this is generated, will be a query that requires to do joins over terms that are constructing applying these ID templates. So in practice, the query that you get is a query that will contain joins over string concatenation operations. And the database engine is not able to do any optimization on this query and is not able to apply to use any indexes that it has in order to compute this query in practice. So although this query is much smaller, when you go and execute this query, it might take much longer to execute. So it's by no means clear that it's better to compute a join of unions as opposed to a potentially exponential union of joins. So this is a query optimization problem. You can, and in fact, that's what we have done. Davide, who was a PhD, who is now an assistant professor in Bolzano, as part of his PhD thesis, implemented a cost-based optimization algorithm that was exactly evaluating the trade-off between these two approaches. And what came out on several experiments that he was running is that in practice, there is no solution that is better. This depends. I mean, this cost model gives you cases in which it's better to unfold the union, or it's better to keep the unions and make a joins of unions. And in general, it's a combination of these two approaches. Okay, so there's no simple solution to this aspect on how to optimize this. All this depends on then having an accurate cost model. So this is a typical database optimization problem, but one that comes up in this setting, and is not the typical optimization problem that you can just give to your database engine. So database engines are not able to compute the optimal optimizations for this kind of queries, to optimize these queries in a suitable way, because these are not typical queries that the database engine is fed. Okay, so they are not able to do this optimizations. Now, a few words about this aspect, because in fact, an approach that helps in getting more efficient queries is the one based on mapping saturation. So the idea is that when we want to compute the unfolding of a query, this is an operation that is done at runtime. So when we issue the query over our ontology-based integration system, this query is processed, is rewritten, and is then unfolded with respect to the mappings. Now, if you do this operation at runtime, this has some cost that you pay at runtime. In practice, however, I mean, there's some computation that you can anticipate and pre-compute, and that makes then the computation of your rewritings more efficient in terms of processing time. And this is this aspect of mapping saturation that I want to mention. And this is related to these two kinds of ontology axioms that we have, those that I mentioned before, sorry, that are related to the hierarchies. These are simple axioms that don't involve existential on the right-hand side, and those instead that are related to the existentials. And these can be treated differently, as I was mentioning before. Namely, we use for those axioms that involve existentials, a rewriting algorithm that is not the one that I was illustrating before, that is a trivial one. It's a more sophisticated one called the three-witness rewriting that was developed by people in Birkbeck some years ago. And we use this together with a mapping saturation technique that uses the mapping in order, uses the mappings in order to, uses the ontology axioms in order to enrich the mappings. So instead of working with the original mappings that have been defined by the user, we use the axioms that appear in hierarchies, so the simple ones, in order to enrich the mappings and get a larger set of mappings. Very simple. Again, it's nothing smart, nothing fancy. It's very simple approach. If you have a mapping that maps a SQL query to a term that has a concept, a class, and this class appears in the left-hand side of an inclusion, then you simply enrich the mapping with the same mapping that has the same SQL query, but now on the right-hand side, it has the class that appears in the right-hand side of the inclusion. This is simply a chase of the mappings with respect to the inclusion assertions in your T-box. Okay? And the same you do for inclusion assertions, domain and range assertions, and for property inclusions. Okay? So you saturate your mappings with respect to the axioms in your T-box. And in this way, you get a richer set of mappings. Now, you get a richer set of mappings, it will still be polynomial. I mean, at most, you get a number of mappings that is equal to the size of the ontology times the number of original mappings that you have. Now, why is this good? You might say, yes, okay, you have traded one for the other. In this way, you have gained much. To some degree, this is true, but the point is that working with saturated mappings gives you additional opportunities for optimizing the mapping itself and pruning the mapping itself. Let's look at a simple exercise. Okay, this is just an example of a mapping saturation. So suppose we have here these few axioms in the ontology. Student is a person, postdoc is a faculty, and so on. We have here these mappings, and you see these mappings access just a few tables: student, academic, teaching, and academic table. And they populate these classes. The idea here is, for example, that in the database we have an academic table where the code 9 in the position type indicates postdocs, whereas code 2 in the position type, the position attribute of the academic table indicates for professors. It's a typical situation, right? You have a table and there is some attribute that encodes some information that ontologically is relevant, because in the ontology you distinguish between top postdocs and professors. In the table, this is a low-level encoding done through a specific code. Okay, this is a very common situation. Now, if we saturate our mapping by applying, for example, the fact that the student is a person to the first mapping, we obtain a mapping, this number 6 here, is analogous to this one, where we just replace the student class with the person class, and so on for the other ones. Okay, so it's easy to see that if you unfold this set of mappings with respect to these axioms, this hierarchy of classes, and also a domain assertion that we have here, we obtain a larger set of mappings that should then be added to the original ones that we have. Okay, so we obtain a larger set of mappings here. Now, what is the idea behind this mapping saturation? The idea behind this mapping saturation is that we can then use it. In fact, we can, first of all, we can use the saturated mappings together with the existential axioms only and get rid of the axioms that are the hierarchy axioms in your ontology. So we enlarge a set of mappings, but we reduce the axioms of the ontology that we have to consider. The effect is that this rewriting step would be simplified, but the mapping and folding step would be more complicated because we have more mappings. Okay, so in principle, this might not give you, might not gain you much because you trade one for the other. Okay, but there's one observation that we can do, namely that the saturation, you can do it once and for all. You don't need to do it for every query. Whereas the T-box axiom, they are considered for every query that you answer. Instead, the mapping saturation, you do it, and then you can answer many queries exploiting the saturated mapping. So you factorize some common operations that you get when you do query answering. Okay, this is the advantage, one of the practical advantages that you have. But we'll see other advantages, namely the fact that this set of saturated mappings can then be optimized and pruned by exploiting information that you have about your database and information about the queries that appear in the left-hand side of your mappings. For example, the query we have here in the mappings, queries that are specific for academics with position code 9 that populate faculty, and with position code 2 that populate. Sorry, I think there is an error here. Maybe I'm not sure. Faculty, no, faculty. Sorry, faculty is a class high in the hierarchy. Yeah, so exactly. No, that's exactly the point for optimization. So we have here, due to the saturated mappings, we obtain the population of the same class, both for position 9 and for position 2, namely faculty. On the other hand, we have here another mapping, that is mapping number 5, that populates faculty without any selection condition on the position. Now, clearly, this query here is just a more specific query. It's contained in the query that we have here. Okay, this conjunctive query with a selection condition is contained in this one. So this means that if we just use query containment to optimize our mappings, we can actually get rid of this mapping because it populates the same class of the ontology, but just with a more specific condition. So by using query containment of the queries that appear in the left-hand side of the mappings, in those cases where we can, because we can do this if these are, for example, conjunctive queries, as in this simple case, we can, in fact, prune the set of saturated mappings. And we might also have more additional constraints. For example, we might have a foreign key over the database. For example, the one that says that if X is a course that is being taught by someone, then X appears in the first position of the academic table. Okay. So this might be a foreign key that holds over your database. And now the information about containment between the left-hand side queries and the information that comes from constraints that you have on your database can be used to actually optimize the set of saturated mappings. In this case, as I was saying, we can get rid of, for example, mappings number 7, 8, 9, and 10, and also 12 and 13, by using query containment, simple query containment, and also the foreign key. Okay, I think, let me see why we get rid of, yeah, okay, exactly. Teaching is, since we have a foreign key from teaching to academic, this mapping here, which populates the faculty class, is actually subsumed by the mapping number 5 that also populates the faculty using the A code that appears in the first position, which is also the same code that appears in the second position of teaching. So using this foreign key, this mapping is redundant considering the first mapping, and so we can prune it. So the effect of these optimizations is that you saturate your mappings, but then you have opportunity to optimize the set of saturated mappings and get as much smaller set of mappings. So you trade the size of the hierarchies in your T-box, which would affect the rewriting, for a larger set of mappings that then get pruned down. So overall, you get a simple ontology and, in the end, a simpler set of mappings. So these are techniques that, in practice, make the whole process of rewriting and query unfolding with respect to mappings more efficient. And together with other optimization techniques, in the end, this leads to rewriting queries that, rewriting techniques that produce queries that are similar to those that users would produce manually if they were implementing the rewriting over the database directly instead of using the ontologies and intermediate step. Okay. So we are now to the point where when there are these opportunities for optimization, and these opportunities for optimization are given by the presence of constraints in the database, like keys and foreign key constraints. I mean, the other aspect that I haven't mentioned, and I think I don't have time to do it, I have some slides, is using the keys to prune the unfoldings, because you can eliminate many of these joins that would be produced by these unfoldings, okay, due to the presence of key constraints and also of incompatible IRI templates. So this leads in the end to techniques that produce queries that are comparable in size to those that would be produced manually. Okay, let me skip this. Instead, let me say something about this process of designing mappings. Now, the form of the mappings is something crucial in the performance of the resulting system. I mean, it's crucial in terms of performance, but it's also crucial in terms of semantics of the overall system. So the mappings clearly need to reflect the semantics of the data in your data sources and of the domain knowledge that you have in your ontology. So we require that these mappings somehow, on the one hand, allow for efficient processing. On the other hand, capture correctly the semantics of your system. Now, first of all, we can make some simple observations about the form of such mappings. And you see them here. So one is that whenever we write a mapping, we should try to have in the source query, so the SQL query that is part of the mapping, it should have the simplest form that is possible. And this leads to the fact that we should try to write mappings, or when mappings are being designed, one should not try to put a lot of triple patterns on the right-hand side together and populate them with the same SQL query, because this might lead for some of these triple patterns in the right to a query that is more complex than what is needed to populate that mapping. Okay, this is one observation. So it's better to split the mappings into many small mappings rather than having few larger mappings, because the few larger mappings are more likely to contain redundancy and unnecessary complexity in the query on the left-hand side. In particular, this is related to joins in this query. So one should, as much as possible, avoid unnecessary joins in the source query. And yeah, this is what related to what I was saying before. So these atoms should be combined in single mapping assertions only if they really require the same query. And yeah. Also, another important aspect is the form of these IRI templates. One needs to pay attention across a set of mappings to have a consistent set of IRI templates. So when somehow the same objects should be retrieved through different queries and populate the same classes or related classes, one needs to pay attention to make use of the same IRI template, so that really these objects that we construct are compatible in the way they populate the different classes. Now, these are some simple observations that one can apply, but these in general are not sufficient to ensure a good design of the overall set of mappings, especially in complex scenarios. So how can we proceed there? So the idea is to exploit somehow common patterns that appear in data sources. So why? Because in general, we have in the data sources a pattern that occur frequently and that are common because data sources in general follow common design principles that are being applied when the data sources have been developed and the corresponding databases have been developed. So this is related to the presence of typical forms of constraints that occur in relational databases and are a consequence of the database design process. And this is related when we are talking about typical form of constraints, we are talking about key and foreign key constraints, which are the most commonly used in relational databases. And in general, when we have certain occurrences of such combinations of keys and foreign keys in the data sources, certain occurrences are an indication that in your ontology, you want to populate classes according to certain patterns. And we try to identify such common patterns that you find in the data sources and how they give rise to common structures at the level of the ontology and hence to structures that you want to see reflected in your mappings. Now, one observation that one should do here is that the constraints that we are talking about of our data sources might either be constraints that are explicitly specified because data sources, relational databases have constraints that are specified, but very often such constraints are not even explicitly specified. Why? I mean, there are many reasons why database designers or database administrators, in fact, remove constraints that are present in the database for performance optimization or because the data is not clean enough to respect the constraints, although it should respect them because they are constraints that are valid in domain. There is some dirty data that would violate the constraints and therefore database administrators, in fact, remove the constraints from the database engine, or they're not present because there are other mechanisms by which actually these constraints are enforced over the data. For example, because the database is access to specific applications that ensure themselves that the constraints are satisfied. So there is no reason to enforce additional constraints in the database because this would be you pay. So this has a penalty in terms of performance of the database engine. So, however, these constraints semantically hold over the data, and therefore it's important that in such mapping design process, they are actually taken into account. So one should not just look at explicitly declared constraint, but also at constraint that, for example, could be mined from the data using data profiling techniques, okay, which analyze the data sources, relation to the data source, and try to extract various kinds of dependencies, keys, foreign keys, functional dependencies that hold over the data, and they can be taken into account in the mapping design process, and also actually in query optimization for the query writing. So yeah, this is related to the fact that when databases are designed, one follows some conceptual modeling principles that are applied in the database design process. And this means that the database schema that one actually has available actually reflects conditions that hold in the application domain. And often the design process is done using some semantically rich models. For example, entity relationship diagrams are often used in database design. Now, one problem in this setting is that these models are used during the design phase of your data sources, but then they get lost when the actual databases are deployed. So often the whole information that had been acquired and was present about the domain gets lost when the database is deployed. However, this information is not, it's lost in the sense that it's not, it might not be present anymore, but it's still reflected in some form or another, either explicitly in some database constraints or possibly in the structure of the data that respect certain design principles, because, for example, your database is normalized. Okay. So this is this observation. So we have in our database often footprints of the design process that led to the development of a specific database. And the idea is to exploit this information. So to make use of this information in order to support the mapping design process. So, which means that we should take into account various kinds of information. First of all, the relational schema with all the constraints if they are present. Also, somehow the conceptual schema that is at the basis of the relational schema that we are working with. data that is stored in the database when we have access to the data. This is not always the case. There are situations where one has direct access to the data in the process of design. Some other situations you might not have access. But if you have data stored in the database and you can access it, and you can, for example, profile this data, this might give you additional useful information. And also possibly domain knowledge that might be present in the whole, so might be present in the heads of the people who carry out the design, or it might be already present in some ontology axioms that are available, because we might work already with a domain ontology that is available when designing the mappings. Okay, so all this kind of information can be taken into account. And I want just to give you an idea of how this is done by describing an approach based on mapping patterns. And what is the idea of such patterns? These patterns take into account these various forms of information. That's what is listed here. Okay, so they rely on the database schema, the ontology when present, and the mapping that we might have between the two. So this is part of the pattern specification. And also the conceptual information about the domain of interest. So I have 10 minutes. I can show you one or two patterns. Now, one observation is that as I was mentioning before, these patterns might just rely on schema level information that is available, or they might also rely on data level information when that might supplement the schema level information. And in fact, the patterns that we specify have a schema version that assumes that the specific constraints, keys and foreign keys, are explicitly present, but also a data version where these constraints might not be explicitly present, but might be derived or available from the underlying data that might be accessible. There are also some patterns that just rely on the data, that require somehow data access. I will show you one of those. Yeah, okay, I think this is not needed. I'm going to use primary key constraints, and foreign keys. The primary keys are represented in the usual way using underlining attributes. Foreign keys are represented in this way. This means that T1 of A is included in T2 K. Yeah. Also notice that when I draw this, when I write this information, keys and foreign keys, the boldface attributes are not a single attribute. Let's say this could be combinations of attributes in general. Okay, I will not show everything. Let me just show a few simple patterns. I have here several ones. But, I mean, I start with the very simple one because this is almost trivial, but that's one that occurs frequently. So the idea is that you have a simple table in your database that has some primary key attributes and some additional attributes. Now, often this information corresponds to what? It corresponds to a conceptual model that was at the basis of this table that was that contained some entity in which these attributes that make up the primary key of the table were identifiers for that entity, and there were some additional attributes that contributed to this entity as well. Now, this is a very simple situation that leads to a situation in which in your ontology you have a class that corresponds to this entity. Okay, you have some data properties for this class, and these data properties correspond to all the attributes of the class, including the primary key. So for each of the attributes that make up both the primary key and the additional attributes, you have a data property in your ontology, and you assert that the domain of this data property is specifically the class that corresponds to this entity. And now what is the mapping? The mapping is very simple. It just queries this table, okay, and creates for each tuple in this table an object in the class. And how is this object identified? It's identified through the primary key attributes, okay? So, and this is the mapping says this, okay, extract from the table. The query is just the one that extracts the whole table. Construct, use the key attributes, which are the answer variables of, which are part of the answer variable of the query that queries the whole table. Use them to construct instances of this class and assert them to be instances of this class. And in addition, assert that the instance of this class have the values of the various attributes that make up both the primary key and the additional attributes as data properties for the corresponding data properties. Okay, so it's very intuitive. What is written there is what I was just saying. Just a very simple example. Suppose you have a client table with social security number, name, date of birth, and hobbies in your database. You can map this to a client. You can assume that you have a client class. Okay, so the target contains here the client class. You have, for each of the attributes, you define a data property. So you will have the social security number, the name, the date of birth, and okay, the hobbies, I don't have them. Yeah, okay, because you might not, in your domain, not all the information might be relevant, okay? In your ontology, you might not be interested in the hobbies of this person. So although you have a table with many additional attributes, some might not be relevant for your domain. For example, here, the hobbies are not relevant, so they are not mapped, okay? So we have here mapping that just queries this table and populates the class and the corresponding data properties. Very simple, okay? The key point is we use the primary key to create the object identifier. And we use here, that's also something common, we use here a prefix that becomes part of the name of this IRI that is somehow related to the class. So I use here for the client class, I use a prefix that reminds me of the fact that here these objects are client objects. Okay. Now, this was the simplest pattern that you can imagine. Here you have a slightly more involved pattern. This is a common situation. You have three tables where one table has its primary key that is split into two parts that are foreign keys towards the primary keys of two other tables. Now, this is a typical situation that would result if you started from an ER model where you have a relation that connects two entities. The primary keys of the two tables that I've called here TETF correspond to the identifiers of these two entities. The two tables have additional attributes that correspond to additional attributes of the two entities. And here, this schema would lead to a relational design that is made up of these three tables. Okay, so we can have a pattern that reflects. Sorry, I clicked on the wrong button. So we have a pattern that reflects exactly this situation, okay? So we assume that we have already used the previous pattern to map these two entities, okay? And that map the two tables T and TF according to these two entities. So now I just specify the additional part that corresponds to this relationship, okay? So for this relationship, I have just a source query that queries this table, and I use, since this is a binary relationship, I use an object property that is inspired by this relation that connects, that is used to connect the two classes. So I have here an object property that has the first class as domain C and the second class as range, and I assert this. And here I populate this object property with the objects that result from the objects obtained from the two tables T and TF. Okay, and here you see the coherence between this pattern and the previous one, because if I mapped before this table T to objects where I used KE as to construct the IRI of that object, now I need to use the same primary key to construct the object that I use here in the in the object property. Okay, so this mapping must be aligned with the previous one, otherwise I would get something wrong in my ontology. Okay. Let me just show another one. Yeah, okay, this is an example, but you can easily, here we had the client table of before. Suppose we have also a location table, and now we have a table address that says that the client is in a certain location, okay? And yeah. And here we have this situation where we have the foreign keys, right? So we have the foreign key from this the address table towards the client and location table. It's exactly the situation that we had before, and we can use this mapping here to populate, in this case, an address property, okay, with the client and the location. In this case, the location is constructed using the two attributes that make up the primary key of the location, the city and the street, okay? And here I've used the prefix that is this one. Let me just show a slight variation of this, and then I'm finished. It's the one where, So this is related to this fact that we need to pay attention that we align the patterns that come from different components of our relational schema. So now suppose that I had a table T and TF as before, and now I had TF with the primary key KF, and now I have a relation similar to before that has two foreign keys, but now this foreign key is not towards the primary key of this table, but it's towards an additional key of this table. Okay, this is also a common situation. So I suppose here I have an additional key, and for some reason the primary key, the foreign key goes to this secondary key, not the primary one. Now, when I define this pattern, I need to pay attention to this. And you see, this is a situation where in order to get so since when I was mapping this table, I was using this, the primary key to construct the objects in the class CF, okay? And now you need to be coherent. And if I want to connect objects, so I want to connect objects of the class C coming from this table with objects of the class CF coming from this table, I need to get access, I need to retrieve the primary key that was used to construct the objects for the class CF. And that's why in this case I need a join between the table TR and the table TF in order to obtain the attributes of the primary key TF. And then I can use this primary key to construct the object that I use here in the object property. If I didn't use a join here, I would construct an incoherent ontology. This is an example that shows that in this case I need a join, so I need a join between these two tables, whereas in the previous case the join was not needed. Okay, here in the previous case I don't need a join because the primary key, the foreign key is towards the primary key. Okay, so this is a typical example that if one doesn't have knowledge of how things work, one gets wrong. And we see this with designs of mappings that are, for example, that use a join in this case where the join is not necessary. Clearly, using a join here creates just a more complicated query that is more complicated than necessary. Okay, that's what I wanted to say. Let me just go to the end. I have one brief summary slides. I mean, there are more complicated patterns that occur. It's a bit slow in advance. Okay. Obviously, no. I mean, I did not. I mean, it was not my intention to present all these patterns. This is it's not that I was. I hope to show you one more, but yeah. Okay, I think this is also additional considerations. Now we have conceived diverse scenarios of designing such systems where this pattern can be useful, depending on what is the information that you already have and what is what you want to produce. Okay. I think we can keep this as well. We are working on automating the design process, and this is using the patterns is a way to support the design process. It doesn't want to advance. Ah, yeah. Okay. Yeah, I think I've given you a slight, brief impression of this approach to ontology access and so ontology-based access integration of data sources. And there's it's mature in the sense that it has been studied, the foundations have been well investigated, there are mature systems that are being deployed in a commercial setting. It's not yet mature in the sense that it's widely adopted, I should admit this. This is an effort that we and other people in the community are trying to do who are working with this kind of technology. So this is not yet a technology that is recognized as in the general data integration scenario. Okay? Although it has a lot of potential for specific situations. We are not saying that this is the solution that fits all problems in that setting, but there are many scenarios in which this is a good approach. Yeah. Also, I mean, one other work that we and other groups are doing is tailoring this technology towards specific scenarios, the finance domain, the medical domain, and so on. I mean, by exploiting, relying standard ontologies and extensive domain knowledge that are available in these domains. So this is also so developing verticals in the various domains. The performance issue is still something that is being worked on, also because it becomes more and more important to support not only relational data, but different kinds of data. Graph data, tree structure data, temporal data is an important aspect. There's a lot to say about this. Yeah. Thank you. Many people with whom I worked in various places. And with some, for example, with Avidor and Roy, we're working on the mapping pattern, and Roman is involved actively in the development of the OnTop system. I didn't show a slide about OnTop. I mean, I should have shown, but I don't have it. And yeah, I mean, the foundations have been developed with the group in Rome, led by Maurizio. And in Bolzano, several people went through. Some are still there, some have moved and are continuing to work. Some are doing other things, but yeah, thank you.